Greetings, everyone. Time to talk about law of cosines now. This is a continuation, sort of, from the last lecture on law of sines. Law of cosines and law of sines really work well together. Okay? So, law of cosines comes from a very similar type of idea as law of sines. Any triangle I have, I can use an altitude to split it into two triangles that are right triangles. And then from there, I can use known properties to build something that allows me to use trigonometry with a non-right triangle. In this case, I'm using the altitude to split it into these two right triangles on either side here. And I'm splitting the bottom side, which was altogether C, into C minus X and X, right? So some portion of it, X, is being cut off, and then C minus X is the leftover portion. Okay? From the right triangle on the right, I can set up a cosine ratio. X over B is the cosine of angle A, which tells me that X is equal to B times cosine A. Also, since it's a right triangle, it has to obey the Pythagorean theorem. X squared plus h squared equals b squared here. All right. Now, the left triangle is where a lot of the magic is going to happen here, right? I have the Pythagorean theorem for the three sides on the left-sided right triangle there. So a squared being the hypotenuse, right, equals c minus x all squared plus h squared. And then what I do is I FOIL out, I multiply out the c minus x times c minus x, and I get c squared minus 2cx plus x squared, plus the h squared that was already there. Okay? But, as we already saw, x squared plus h squared is equal to b squared. And x is equal to b cosine A. Now what that does is it just basically gets rid of all of the x pieces in there. And so now I have nothing but original triangle information there. And so I rearrange it. A squared is equal to b squared plus c squared minus 2 times b times c times cosine A. And that's actually one form of the law of cosines. Should look very, very familiar to you. If you don't have the minus second half of that piece there, it looks a lot like Pythagorean theorem. In fact, law of cosines can be thought of as a more generalized version of Pythagorean theorem. It's a version that works with all triangles instead of just right triangles. And it involves the cosine of some angle that's inside of the triangle. Okay? Now notice the pattern. The side that's isolated and squared is the angle pairing that goes in the cosine, right? Because remember, angles and their sides that they're paired with, like angle A, side A, they're opposite, right? That was just like law of sines. The angle side pair are on either side here, you see. And then b squared, c squared, and b and c again. You can rewrite law of cosines using any combination of the letters, any combination of the sides of the triangle. And the only thing that changes is the angle whenever one of the other sides is isolated on the other side by itself. Okay? Now, the format that the law of cosines is in here is perfect for solving for a missing side. For example, if I know B and C in angle A, I can punch all of that in and just compute side A. Okay? So on and so on. However, if you solve for the cosines in each one, you can consider something of an alternate form of law of cosines in these formats here. These are the same things as what I have over here. All I've done is I've added and subtracted a few things and divided something to solve for the cosine in each formula. Okay? And basically all that does is it sets you up to solve for an angle instead of solving for a side. So we have the alternate forms of the law of cosines here just to speed up the process when we want to solve for an angle. You don't usually have to bother memorizing the alternate forms, but if you use them enough, they tend to stick to you. Okay? If you can remember this version of law of cosines, I mean, it basically comes from that anyway. Okay? Something else that comes up when dealing with law of cosines that we won't bother going through the whole proof here fill up, a lot of space. But Heron's formula for the area of a triangle, okay? Area of a triangle is going to be equal to the square root of P times P minus A times P minus B times P minus C, where A, B, and C are the sides from the triangle, right? A, B, and C are the sides of the triangle. And P is what we call the semi-perimeter. That's 1/2 times the perimeter of the triangle. The semi-perimeter, half of the perimeter, okay? And that gives us a really awesome way to compute the area of a triangle. All you need is the 3 sides, and that's actually very powerful. Instead of actually having to find the height and do 1/2 base and height, all you need is the 3 sides, and you can just plug it in and crunch out the area. And that makes it a very powerful area formula also for larger shapes. All of the polygons that we deal with in mathematics can be broken down into triangles. So one way or another, you can find the area of all kinds of shapes with this powerful of a formula that can find the area of any triangle, and all you need to know is the sides. Okay? First example. Solve the triangle. Remember what that means? Here's some information about a triangle. Find the rest of the information such that all of it has to be true, right? So I've been given 3 pieces of information, which is minimum for doing one of these problems. And it's not all angles, which is good because that wouldn't be viable. It is, however, side angle side, and that's important to remember. The reason why we're not about to use the law of sines, okay? If you have a side angle side situation, which you can tell we do, look, we have little a and little c and big B. I have little a, little c, and big B right here, right? So notice I have a side angle side situation, which is going to require the law of cosines. I'm not going to be able to find any side angle pairs, big A, big B, little b, whatever, from the original information because of the way that's set up. I can't subtract to find any angles. I can't do anything else to find any other sides. So law of sines is out. I can't use that with the current situation. Maybe later, right? It requires law of cosines thereby. But law of cosines is perfect for this situation. If I know 2 sides and then an angle in between them like that, that's exactly the original setup of law of cosines. So look, I'm going to set up with the law of cosines formula where little b squared is by itself. That's a squared plus c squared minus 2ac cosine big B. And it's already all set up. All I need is little a and little c and angle big B, right? And then I can just crunch what side B is. It's squared here, so I'll actually have to square root both sides. But look, here's the setup. Square root 346 squared plus 457 squared minus 2 times 346 times 457 times cosine 65 degrees. So I'll punch all of this in to my handy dandy time saver. Squared 2 times 346 times 457 cosine 65. Make sure you're in degree mode, right? Square root. And I'm getting 441, basically 0.5. So approximately 441.5, and it's measured in inches, right? So inches. All right, so we found little b. From this point on, we actually have a choice now. I could continue using more laws of cosines and finding different angles, or I now have a pair. I have big B and little b as a pair, a side angle pair. I could revert back to law of cosines, which a lot of times ends up being a little bit faster, just depending on how you like setting up your equations, right? Formulas. So let's do that. Let's bounce back to law of sines, right? At this point, if I want to solve for angle A, I will do sine of 65, which is big B, over little b, 441.5. And that's equal to sine of A over little a is 346. Okay? Now I know you're probably thinking the same thing I am. When we were solving for angles in law of sines, it could possibly have two answers. Good news. When you've come from a law of cosines and you've been building this already, these always come out to have single answers. And you can check both of them if you want, but the way these things are built out, it's going to happen with just the one answer every time. And to support that, I could have chosen the law of cosines to solve for an angle. And the way cosine is set up, you're only going to get one answer every single time, or well, unless you get a no solution, right? You can't get double answers when you're doing a law of cosines, because cosine, the other side of it being positive is a quadrant 4, and that's way too large, right? So the only possibilities in cosine that you'll get is either 1 or 2, not both, okay? Because cosine would be positive or negative. So anyway, back to this. If I go ahead and solve this the way we did in law of sines, I will multiply the 346 over to this side, and my A angle is going to end up being the inverse sine of that. Because I'm using the reference angle as my quote-unquote first answer, okay, that would have been A1 from the law of sines problems that we were doing, right? The A2 is going to be too big to work with the rest of the angles in the triangle, okay? And I'll show it to you real quick. But let's compute this one first. This was technically the reference angle answer to this question. So I'm going to be doing inverse sine of 346 sine 65 divided by 441.5. And of course this is going to be a little bit off, right? Because that was a bit of a chop when we did that one. But it should be pretty close. I'm getting 45.25. So let's say 45.3. Okay, now I'm going to put the little or here just to sort of fluff what I was talking about before. Okay, try it out. This is the reference angle from quadrant 1, right? That's the quadrant 1 answer from the law of sines. What would the quadrant 2 answer be? Right? 180 minus this, because if this is a reference angle in quadrant 2, you'd have to do 180 minus the 45.3. So let's see, 180 minus 45.3 would be 134.7. Right? Those are the two possible answers in general to this sine question. Okay? But even though this could fit in a triangle by itself, if I add 134.7 to 65, it's already bigger than 180, which means it can't work in any triangle, right? So this is not going to work. And therefore, this must be my angle A, right? And of course, I have angle B, 65. If angle A is 45.3, then angle C is just a subtraction away. So angle C is approximately equal to, let's see, 45.3 and 65, that's 110.3. So 180 minus 110.3 means that C should be approximately equal to 69.5. 0.7. Okay. So I've got the missing pieces of information here, right? At any point, if you're doubting if one of these angles is correct, you could also switch over to using the law of cosines to check it. Okay? If you want to, we can write that down real quick. Look. The law of cosines alternative here, I'll put a little or. To look for A, I could say cosine of A is equal to, and I'll be using that alternate form that we talked about. That was b squared plus c squared minus a squared over 2bc. Okay? So if I punch up those sides, right, push them in, we have b squared, which we just found is 441.5 squared, plus c squared, right, 457 squared, minus a squared, so 346 squared. And then I'm going to divide that by 2 times b times c. So in your calculator, be sure you put a parentheses around that. 2 times b, 441.5, times c, 457. Okay, so I've got 0.703 for this part right here. So cosine of A should be approximately 0.703-ish. 4-ish. Take an inverse cosine of that. And I got 45.25, right? Which again supports the quadrant 1 angle that we got there, the acute angle that we got there. Okay? So you can do law of sines, or you can do a law of cosines. Either way, you'll get that other angle, right? And then of course, subtract to get your final one. Okay, a throwback from the law of sines time. It says find its area. Well, I have all 3 sides, and I could use that new Heron's formula, but wait, there was a nice formula from the law of sines chapter. We said area of a triangle was equal to 1/2 BC sine A. And of course, you could do any arrangement of that. You could do AB sine big C. You could do AC sine big B. And that's actually the one we need in this case. So let's rewrite it. We could do AC sine big B. The only stipulation was that it was 2 sides and the angle in between. And it just so happens we started out there at the very beginning. So I don't need to do anything extra for this area. I'm just going to punch up what we've already got there. The area is equal to 1/2 times A, which is 346, times C, which is 457, times the sine of 65 degrees. Okay, so what is my area going to approximately be here? Let's find out. I got 1/2 times 346 times 457 times the sine of 65 degrees. All right. So I've got 71653.6 basically. And these were measured in inches, so this is going to be square inches. Okay. All right, one more example here so we can go at the other combination. Here, solve the triangle again, and we'll also be doing the area again as well. But notice what I've got here is side, side, side. Also a formation that cannot be done in the law of sines because I don't have any way of forming a side angle pair in the triangle. Okay, so law of cosines it is. I actually kind of prefer that one myself anyway. It feels I don't know, some way more familiar and a little bit cleaner. But side, you're pretty much required to do law of cosines, okay? However, I'm going to be doing the alternate form first because I'm looking for angles here, right? So let's do that. Pick any angle you want to solve for, right? Whether it be angle A, B, or C, it doesn't matter. Let's do angle B. Cosine of B is equal to A squared plus C squared minus B squared over 2 times A times C. There's our formula. Okay? So then I'm going to set that up. 21 squared plus 30 squared minus 17 squared over 2 times 21 times 30. And that's equal to the cosine of B, right? So to find angle B, I'm going to be doing an inverse cosine of that. Like so. All right. Now be sure when you're punching this in the calculator that you're putting those extra parentheses in there. What do I mean? The calculator, if you're going to do this all at once, it needs to know that all of this is the numerator because of the additions and subtractions, and it needs to know that all of this is the denominator. So if you're going to punch it all in at once, you need those extra parentheses in there to emphasize what you're doing. Okay? To group it, emphasize the grouping. I have 21 squared plus 30 squared minus 17 squared. And then my denominator, 2 times 21 times 30. And that's inverse cosine, yes. 33.39, so let's say 33.4 degrees. Okay. Now we're back in the position that we were in the previous problem. I have an angle side pair and I have some other sides. I now have options. If you prefer at this point, you could go straight to a law of sines and set up the different sine ratios and solve for the missing angle. Or we could continue with another law of cosines that's set up exactly the same way. Since we're already in this groove, I'm going to continue with law of cosines set up. Let's go ahead and set up the other ones. Angle A is going to be the inverse cosine of, and then it's going to be B squared plus C squared here. So that's 17 squared plus 30 squared, and then minus A squared divided by 2 times B times C, right? We'll crunch that one up. And then angle C, very similarly, is going to be inverse cosine of A squared and B squared. So 21 squared, 17 squared, minus C squared, 30 squared, over 2 times A times B. Okay? Now, one little thing I want to point out on this is the 21 squared plus 17 squared minus 30 squared ends up being a negative number. So you're doing an inverse cosine of a negative number. And don't forget what that means. Arc cosine is defined for negative numbers in quadrant 2. This is going to give me an obtuse answer, right? Which is okay. Let's go ahead and crunch both of these up, and then you'll see that they should add up to 180 degrees. So I just hit up on my little cosine daily here. I've got 17, 30, minus 21. And then my denominator is 2 times 17 times 30. Okay. So I get 42.833. So 42.8 degrees. And then I do it one more time. I've got the 21 and the 17 minus 30 there. And then divide by 2 times 21 times 17. I'm getting 103.77, so we'll say 0.8 degrees. Right? And I think you'll notice with me here, if we add these up, right? 33 and 42 gives us 76.2. The 0.2 here gives us 104, and then 76 and 104 is 180. These do add up to 180. I do have the actual angles to this triangle now. Okay? So there's many ways that you could have done this. This is just good practice for us to talk about how I could use the law of cosines directly to get these angles. Okay? Now, on the other side here, talking about finding its area. It's always best to use original information. I could do the 1/2 AB sine C or whatever other formula there is. However, this one was perfectly set up at the beginning for that new Heron's formula. I've got the 3 sides. Let's practice that one. Start by finding the semi-perimeter. That's going to be 1/2 of the perimeter. In this case, 21 plus 17 plus 30, right? So I've got 38 and 30 is 68 times 1/2 is 34. So then my area, according to Heron's formula, is going to be 34 times 34 minus 21 times 34 minus 17 times 34 minus 30. So let's simplify that a little bit, and then we'll punch it up in the calculator. I've got 34 times 34 minus 21 is 13. 34 minus 17 is 17. And 34 minus 30 is 4. And this is something that you can punch up pretty quick in the calculator there. So let's do that. Square root 34 times 13 times 17 times 4. Close your square root. And I have 173.3666. So approximately 173.37. This was in feet, so this will be in square feet. Okay. I hope that this has helped you further your skills using law of sines and law of cosines to solve for non-right triangles.